Okay, so for an application of mass moment of inertia, the famous is the flywheels. Okay, and then flywheels have higher rotational inertia. We can say rotational mass. Okay, this one you can call it as a rotational mass, but be careful that it's not a scientific term. Okay, so it has a higher inertia. Higher inertia means that it is difficult to stop it. Okay, or in other words, you can say that it has higher energy. And maintains it. That's very important. It maintains the high energy. That's the reason that we are using flywheel for an engine. We are using flywheel for a pump in petroleum extraction. We are using the flywheel in toy car. Because it has a higher energy, it keeps that higher energy, and that's the reason that the toy cars, for example, with the flywheel, they move very fast. And then this one as well. And then it has one more advantage, that it brings the equilibrium to the system. Okay, that's another advantage of flywheel, but that's not our topic today. But we are talking about the rotational mass, inertia, etc. But it has an advantage that it brings equilibrium to the system. And then this is also called the mechanical battery. Okay, that's the flywheel. Okay, and then as I said, the rotational inertia of the body depends on the size, axis of rotation, and the shape. This is another shape that we have. So then the question comes, how to find the I value? Okay, to find the I value, you can use the differential equation. Integral equation. The first thing is that integrate yourself, which is, we'll not do that. And the B is that use tables. That's what we are going to use, these tables. And these tables will give us enough information, and then we will do the things easily. And then I should tell you that the integrate yourself, it will be just to reinvent the wheel. In not all of the cases, but most of the cases, it's like you are reinventing the wheel. There's no need to do that. Okay, then you can use the tables that have the existing relationships instead of wasting your time on looking for the integral relations for the objects. Okay, and then let's go back to our problem here. So why this one moves faster than the other one? So the answer is that the I of the hollow cylinder is higher than, let's say, greater. Yes, it's more greater than solid one. So since it is greater, it moves slowly. Okay, compare with this one. Higher mass goes slowly. Higher rotational mass goes slowly. Okay, so then the final thing that I will talk about is, how integral is done. We will not do integral, but I will give you a logic how it is done. Let's say how I is calculated. Okay, so the logic is that first you choose a axis of rotation. Okay, say that I am choosing this axis as the rotation, and then this body, say that rotates that way. Okay, And then what we do is that we take first a small mass, a chunk of delta m1, and then the distance from this point, the center of it, to this axis, that is the r. Okay, and then what we do is that delta m1 into r squared plus the second part. We take again another mass here, so I will just show a little bit of it, and then the rest is not our topic here. Again, this is r, and then plus delta m2 r squared. Similarly, delta m3 r squared, and then plus delta mn r squared, and then mn is this mass, the final one. And but that one is, I mean, all of them is like this, yes, three-dimensional. And then this one has a radius of r. Okay, and then if delta m is small enough, then you will have that delta m1 is delta m2 is, and this way delta mn. And that's the reason that this is, I mean, this is I actually, we are calculating the I. The I value will be equal to then delta m1, that will be delta m plus delta m plus delta m plus delta m into the r squared. And this all as the m total of washer. Okay, and the final result comes that I is mr squared. Okay, that is how you do this I calculation, but this one is very simple case. But for more complex cases, you will do this one, the r squared into the m. Okay, that's how you do for a more complex cases. And then next recording, I will talk about parallel axis theorem.